A quick update based on my initial grading of Project 2, and I want to point out that if you get a Project 2 back and it's really crummy, even if it's not really crummy, you're welcome to resubmit it, and I'll try to give you some points back based on that resubmission. There's a few things that I just want to emphasize. I gave feedback for Project 1, but I think some people didn't get it. So one is, it is poor if the result of the project is not stated, this one right here, in the abstract. So abstract is just a sentence or two describing what you measured and the result you got. So maybe a little bit about how you measured it, but it's very brief, but the result needs to be there. The description as a separate paragraph, labeled description. It would be very helpful if you could have abstract, description, schematic, background, discussion. I mean, you don't have to have all three of these. You should definitely have a schematic. But background and discussion, I think, could be like one section. It's what do I need to know to understand what you're doing? What's the background information I need to know to understand this circuit? Okay. Circuit function is pretty good. Most people are validating what they did. Most people are presenting results in a reasonable way, making sure the units are there, making sure the labels are there. But a lot of people in the conclusion are not putting the result again. So the result needs to be there, and hopefully some measure of uncertainty. So how well do you know that answer? And I'll talk about that more here in a second. But I just want to make sure it's clear that I really do go through the rubric piece by piece, and I expect you guys, I want to get everybody in this column, right? So just make sure you're doing everything in this column, and everything will be fine. So the next bit is the data analysis. Oh, wait, one other thing. Hang on. Before I get to data analysis, code. So let's say, actually I'll do it this way. I've got some code here. I've written this lovely Arduino program, and I want to share it with my instructor because it's an important part of my project. So the thing is, I have a markdown cell, you know, that has this is whatever. This is my great project, and I'll format this nicely so that this is what it's whatever about. If I just type the code in there like that and render it, it comes out garbage. I can't read that. So what I want you to do is make sure when you enter the code that you indent it like so. And notice it changes color, and then when you render it, it comes out looking like code. So please don't just paste code into a markdown cell and not indent it so that it doesn't get rendered as code. Okay? And let's see, what's the other part? Right. So if I run this code, I've set up the transistor project. Of course, you guys did this in the lab, but I went ahead and set it up in Tinkercad just so I could show you the concept here. I've got 3 voltages. I'm measuring the voltage driving the circuit. That's V1. V2 is the voltage of the base of the transistor. V3 is the voltage of the collector. And what I want you to notice is that not all the data is really useful in this analysis. The problem is I'm analyzing the linear region where the collector current and the base current are proportional to one another. And there's only a relatively small part of the data that lives in that region. You can see the drive is increasing over here on the left. There's the drive going up. The voltage on the collector is dropping. Now this is the region that I'm interested in. But as the voltage on the collector drops, the current through the base goes up. Eventually, and it's not going to take too much longer here, I don't think, the voltage on the collector is going to hit rock bottom. It's basically going to get close to ground, and I can't measure anything beyond that. In other words, the collector current can't get any bigger because the collector voltage has hit its lowest possible value. Here we are down at 125 millivolts. You know, it's not going below 100 millivolts probably, no matter how hard I try. And so I'm driving and I'm driving harder and harder and harder, but there's just nobody home. So I might as well stop. There's no benefit of continuing to push. What I want to do is go ahead and select this data. So let's just scroll down here. I'll copy it. We'll paste it just into a text document, or you could paste it into Excel, however you want to do it. and I'll just save that guy, and I'll call it data.csv. I guess I already got one there called that. I'll just replace it. Okay, and then I want to pop back over to my, let's see if I say %ls star.csv, have I got it there? Oh, I'm in a different darn directory. Hang on a second. Okay, I just switched directory. Let's see what if I have my data. There it is. My data.csv is there now. So I'm going to, let's import pandas as PD, and let's go ahead and matplotlib inline, and then I'll import matplotlib pyplot as PL. Okay. Okay, so there we have our tools basically in place. Oh, I want to also, daggone it. Okay, I want to do a curve fit here in a second. So there's one other thing I want, and that is I want to say import from scipy.optimize import curve fit. Okay, so let's get the data. So I'll load into a data frame. I'll say pandas loads or read CSV. Read CSV data.csv. That's it. And then let's just look at the thing to see what it looks like. Okay, so I've got my 3 voltages there. Now, one thing I like to do is just to say df.plot. Let's just look and see what's there. So here's the collector voltage dropping. Here's the drive voltage, V1, just marching higher and higher and higher because we're driving the transistor. And here is the base voltage on the transistor. Notice it's a diode, so it caps out at 1 diode drop. So really, it's this region here where there's a gap between the drive voltage and the diode, the base voltage of the transistor, and that's the same region where the collector voltage is dropping. So that's where I want to do my analysis. So it looks like I want to go from about, what, 32, and this is just the index, right? This is the index. It goes from about 32 or 33 up to maybe 50 at the most. So, well, hang on a minute. That means I should be able to say V drive equals df.v1, and I want to go from, let's say, from 33 to what, 40 or 50. Let's just say 50. Okay, and then V base is going to be df.v2 33 to 50. And V collector is going to be df_v3 33 to 50. Now the other thing I need to do, of course, is I need to multiply by 5 volts and divide by 1023. So I'm just going to add that onto each of those. And what that does is that's going to convert everything into volts. So now I could say pl.plot. Let's say I want to take the drive voltage as the x coordinate and the collector voltage as the y coordinate. And there you can see, now it's a little bit jumpy, and that's mostly because it's Tinkercad, or maybe I took the samples too quickly and didn't let things settle down long enough. But you can see I've got something approaching almost a straight line there. My point is, you don't want to analyze all the data. It's only the data in this range, and you can use slicing to pluck out the data that you actually care about. Okay, does that make sense? And now I can do, let's actually calculate the collector current. So IC is going to be, what is it? It's 5.0 minus VC. That's the difference between the power supply and the collector voltage, but I've got to divide by that collector resistance. I'm thinking that was 5K. So we'll make that 5,000 ohms, and let's look at what we got there. Yeah, that looks reasonable. So that's Those are then milliamps, right? Those are milliamps. And then what about the base current? So IB, that's going to be the drive voltage, VD, minus the base voltage, VB, and then I've got to divide that by the base resistor, which was 100K. So I divide that by 100. Let's look what IB looks like. Yeah, that looks that looks kind of reasonable. It looks like let me just double check my resistance there, make sure I've got that right. Yeah, that's 100K, brown, black, yellow. Okay, so these are milliamps as well. So here we're actually looking at pretty tiny voltages, and yeah, that looks all right. 3.3 volts. Yep. Okay. So then I want to plot pl.plot. Let's plot IB as the horizontal coordinate, IC as the vertical coordinate, and you can see that I've got pretty nearly a straight line. So I could dress this up a little bit. Let's draw it with blue dots. Let's give it a title. Collector current response to base current, something like that. X label is going to be base current in milliamps, right? Y label is going to be collector current in milliamps, something like that. Okay, and then I've got a decent looking graph there. Let's go ahead and let's do a fit. What's the function going to be? Well, it's a straight line, right? So let's do fit function x m b. I'm just going to return m times x plus b, right? I'm going to curve fit the data that I have. So I want to say the parameters and the covariance matrix are equal to curve fit. What do I pass in first? It's the fit function. Then I pass in the x values, that's IB. Then I pass in the y values, that's IC. And maybe that's going to do it. I don't really need, it's a linear fit, so it should work no matter what. So I'm going to say m comma b equals the parameters. I'll say dm comma db equals, what's it going to be? It's going to be the diagonal elements. You know what? I just realized I forgot to import numpy. So import numpy as np. Okay, then I'll have numpy. So I can say numpy dot square root numpy dot diagonal of the variance. Okay, so now I can let's go ahead. Let's make a theoretical current, a base current, I base theoretical. That's going to be a lin space. It's going to go from IB0 to IB minus 1, and let's go in steps of 10, say. And then let's do IC theoretical. That's going to be my fit function times, I'm going to pass in x is going to be the base current, and the m is going to be the slope, and b is going to be the intercept. So the ones I got here from the fit. Okay, and then let's plot that. pl.plot base current theoretical, collector current theoretical, and let's use a red line so that we can tell the difference between the fit. Oh, it doesn't like something. What was it? Ah, that's the problem. This should be IB theoretical. Boom. Okay. Sorry about that. Okay, this should now work. And now we have a fit. Let's go ahead and print out the slope and intercept. So if I say print slope equals, and then we'll say percent 5.3f, and then put in m, I better say plus or minus percent 5.3, and we'll put in m and dm. And then we'll say print intercept equals percent 5.3 plus or minus percent 5.3. I hope 5.3 works. We're going to find out. That's B and dB. Doesn't like something there. Oh, left off the F. Okay, now that's a pretty high beta, but realize it's not a real transistor I'm using there. It's a Tinkercad transistor. This one I need a little more precision, so I'm going to go ahead and make this 9.5 and make this 9.5%, 9.5, and that'll give us a little more precision there so we can really tell. It looks like it's pretty close to 0. Actually, it's indistinguishable from 0 because the error is greater than the difference from 0. So it basically goes through 0, has a slope of 289 plus or minus 8. So one of the questions I got is, how do I know the uncertainty in these things? Well, if you do a fit, you get the uncertainty for free out of the covariance matrix. So that's all I really have for you. The main points are, don't just use all the data, identify the data that's interesting, and if you have a straight line or you know what the relationship is, go ahead and do a fit. That's why those tools are for. So please use them. The other one we had in this project was the need to measure a gain. You could take the ratio of the two voltages in that case and show that the ratio is equal to 2. And then you could use statistics, get the standard deviation of the ratio to get some sense of the uncertainty. Or you could plot the input voltage versus the output voltage versus the input voltage and get the slope of that. That would also be the gain. So there's different ways to do it, but I hope this helps you guys see how, at least one way, you can analyze that transistor data. Thanks a lot. We'll talk to you soon.